Welcome everyone to another lesson of chemistry today. Our topic is going to focus some more on polarity. And so we're going to follow lesson 11 in your study guide. So if you'll get out lesson 11, polar, nonpolar, we'll get started. All right, everyone should be on lesson 11, polar, nonpolar. So as the name implies, we are going to address polarity some more. In the past few lessons, we have been looking at covalent compounds, specifically molecules, where we have focused on drawing the Lewis structure of molecules. We have talked about resonance structures, and we have focused on the VSEPR shapes. And now we're going to get into determining if a molecule is going to be polar or nonpolar. But before we do that, I'd like to review polarity in general first. So remember that polarity goes back to this idea of electronegativity. And we talked about that two atoms that are forming a covalent bond with one another are playing a tug-of-war match between the shared pair of electrons. And the element that has the largest electronegativity is winning that tug-of-war match, right? And if an element wins that match or winning that match, there's going to be an unequal sharing of electrons. And that unequal sharing of electrons will lead to what we call a polar bond. Now, if there's an equal sharing of electrons, then it leads to a non-polar covalent bond, right? So what we're going to do is talk a little bit more about this electronegativity difference between two atoms and polar covalent bonds versus non-polar covalent bonds, but then apply it to molecules in determining if the overall molecule is polar or non-polar, okay? So keep that in mind here as we go through this. All right, now we've talked about this tug-of-war match here, and we've looked at this before, and we said that the element that has the largest electronegativity value that's winning this tug-of-war match is going to have a higher electron density, okay? And so because of that, it's going to create a dipole, right? And the dipoles are what's important here. And remember that we're going to draw a dipole arrow that's going to be pointed to the most electronegative atom, which is chlorine here. We're going to put a line there that represents that this is a dipole arrow. And just to remind you that a dipole is where you have basically an unequal of electron distribution within the bond. So part of the bond is partially negative and partially positive, and that creates the two poles, or the dipole, as we would say, okay? And chlorine is going to be that negative charge, or partial negative charge, because it's going to have a larger dipole moment towards that chlorine because it's more electronegative, it's winning the tug-of-war match, and it's going to have a higher electron density, as we can see by this model here, okay? The electron density is much greater on chlorine and much smaller space over here where the hydrogen is. So chlorine, this region is called an electron-rich region, and the other region where hydrogen is an electron-poor region, okay? The bottom line is that there's an unequal distribution of charge, there's an unequal sharing of electrons due to the difference in electronegativity values between chlorine and hydrogen, and this creates the dipole in the bond, okay? So again, all we're doing is focusing on a dipole in the bond, okay? Not the overall molecule. All right, so this is some more models that we're representing electron distribution. And what we're going to do is look at these models and make a decision if there is a dipole or not. In other words, is there's a polar-nonpolar bond that's occurring here. So if you look at lithium and hydrogen, okay, we're going to form a bond between these two elements, okay? Is there a dipole that's occurring here? Well, is there a difference in electron distribution? That absolutely is, okay? Over here, where the lithium atom would be, there is a very small amount of electron density in the bond. And where hydrogen is right here, there is a large amount of electron distribution or density going on. So what we're going to say is that there is a big or an extremely high or large dipole that exists between lithium and hydrogen. Okay. Now the colors that you see do correspond to understanding the dipoles. Where it's really red, the redder it is, the larger the electron density is, and the larger the dipole or the negative, partial negative charge or full negative charge occurs. Okay, where it's more blue is the lowest electron density, and then green and yellow is kind of in between. So what we're basically seeing is that in hydrogen's case, most of the time, the electrons that are between lithium and hydrogen are pretty much belong to hydrogen and less to lithium. In fact, the dipole here is so big that essentially this is going to be an extreme dipole forming an ionic bond. You're not going to really see a really good sharing of electrons here in this dipole. So we would say that lithium hydride is the name of this compound, is ionic and less covalent in characteristic because of the large dipole that is occurring here. Okay, so essentially lithium has transferred its valence electrons to hydrogen. Now let's look at H2 here. Now you have that normal egg-shaped electron density. So, and it's also green color. So what we would say is that the electron density in H is pretty evenly distributed. And so therefore we would say that this is a nonpolar covalent bond between H2. There is no dipole that exists. And that should make sense because both hydrogens have the same electronegativity value. Therefore, the difference in electronegativity is 0. That will result in a dipole. Okay. Now let's go back to HF. We got a lot of red over here where the fluorine is, and some blue over here. So the question is, it looks like we definitely have a dipole, right, towards the fluorine. The problem is we have to distinguish, is this going to be more ionic or more covalent in characteristic? In other words, is the hydrogen transferring its electrons to the fluorine for the most part, or is there a sharing or an unequal sharing that's occurring here? Well, it all depends really on the difference in the electronegativity values, which we're going to look at in just a moment. Because the difference in electronegativity between hydrogen and fluorine is big, but not super big as it is between lithium and hydrogen, this is not going to be a ionic bond. This is going to be a polar covalent bond. And so you're going to get partially negative here and partially positive here. Whereas on the hydrogen over here, this is going to be fully negative, and this is going to be a fully positive charge. And so we have the two ions that are attracted here, and these are ions, the two ions between lithium and hydrogen that forms the ionic bond. Whereas between hydrogen and fluorine, there is a sharing, an unequal sharing, and therefore we get a partial positive and negative charge, and it becomes covalent in character and less ionic in character. Okay. We can also see the egg shape that's not quite as dramatic as with the ionic bond. You can see a very small electron density here and a little bit larger for the hydrogen. And it's blue, but it's not as blue as the lithium is. So it's a little bit better distribution here, as you can see from this egg shape, than it is for the lithium hydride. Okay. Now, let's get into numbers, because that's what you're probably asking yourself. Well, how big of a difference do we have to have in order to have an ionic bond versus a polar covalent bond? Okay, so that's what we're going to look at right now, is those numbers. All right, so if the electronegativity difference between the two atoms is between 0 and 0.4. The difference is not very big. Therefore, it's going to be a nonpolar covalent bond. Okay, if the electronegativity difference is in this range here. For a polar covalent bond, we want kind of an intermediate difference, and that is between 0.5 and 2.0. So if you have a bond and the electronegativity difference is in this range here, then we're going to call it an intermediate range, and therefore results in a polar covalent bond. But if we have a electronegativity difference greater than 2.0 or 2.0 and greater, really we're going to have an ionic bond that's going to occur. We can call this ionic in character. Okay, so there's some numerical values, and you might want to actually memorize those values because they're not going to be given to you for the test. So just kind of think between 0 and 0.4, it's going to be nonpolar. 0.5 to 2.0 is polar covalent, and above 2.0 is going to be ionic in character. Okay, so there's a little bit of a review between polar and nonpolar, as well as incorporating ionic bonding and electronegativity here, and looking at actual differences and creating more of a characteristic in what bond type we're looking at. Is it more ionic or is it more covalent? Okay. All right, so now what we're going to do is get into more of our topic today at hand that we really want to focus on, and that is determining if a molecule overall is polar or nonpolar. Okay, so we can have a molecule that might have polar bonds, but because of the shape of the molecule, the Vesper shape of the molecule, those polar bonds are canceled out or offset or eliminated. And therefore, the actual molecule is nonpolar and there is no dipole that exists. Okay. So what we need to do is look at a Lewis dot structure of a molecule, look at its shape. Okay. In fact, I would draw the Lewis structure, incorporate the shape, the Vesper shape into the Lewis dot structure in order to help you to determine the polarity a little bit better. Okay, so let's look at an example here. We have a molecule of CO2, carbon dioxide. Okay, and if I was to draw the Lewis dot structure, it would look something like this. Now, it is going to have some lone pairs on those oxygens, so I'll actually draw those in there. But as you can see, and as you well know, that the carbon being the central atom, it has a double bond between both oxygens that surround it in the Lewis structure. Now, in order to determine the shape, you have to use those electron domains, and we know that since there are two electron domains, one here and one here, that's going to put these two domains as far away from each other at 180-degree angle. And therefore, its carbon dioxide is a linear molecule. All right, now that's important. The shape of the molecule is going to help determine the overall polarity. And so we need to be as accurate as possible with our shapes, okay, in our Lewis structures. Now, the next thing what I'm going to do is I'm going to look at each individual bond situation between the central atom and the atoms that are bonded to that central atom. And I'm going to see if there's any dipoles that exist within the bond, okay? So the first bond I'm going to look at is between the carbon and this oxygen right here that I'm circling. And I'm looking at this double bond and I'm asking myself, is there going to be a dipole between the carbon and the oxygen? Well, the answer is yes, because oxygen is going to have a greater electronegativity value than the carbon. So therefore, we do have a dipole, and we're showing that with the dipole arrow. And the arrow is pointing towards oxygen, okay? Now, if I look at the other bond, covalent double bond between the other oxygen and carbon, I also are going to have a dipole. But notice that this dipole is in direct opposite of the other dipole, okay? Now, what we have here is what is called a vector. Now, if you do not know what a vector is, a vector has two things. It has magnitude and direction, all right? And a dipole is really a vector, okay? It has a certain magnitude value and it has a certain direction, okay? So in this case, there's a dipole that's going towards the right and another dipole going towards the left, right? For simplicity terms for us, we're either going to have a dipole that goes right, left, up, or down, okay? Right, left, up, or down, okay? Now, here's the key here. Here's the kicker. If both dipoles have the same magnitude, okay, that means they're pulling with the same force. And they are because they have the same electronegativity difference between both of these dipoles, okay? But if they're pulling in opposite directions, one is going this way and the other dipole is going this way, the two dipoles are going to cancel one another out. They're going to offset each other, okay? So because they're going, the two dipole arrows are going in opposite directions or pointing in opposite directions, we are going to say that the overall dipoles eliminate one another, and therefore this molecule has no net dipole and essentially is nonpolar. So we're going to say that carbon dioxide is a non-polar polar molecule, okay? Nonpolar. And again, it's basically because both dipoles are pointing with the same magnitude, but in opposite directions, so it eliminates that dipole, okay? We'll give you some more examples of this, so don't worry. All right, let's look at water, okay? And let's compare this to carbon dioxide. Now, water has a Lewis structure that looks something like this, where it has some lone pairs on the oxygen, and those lone pairs are going to cause these bonds to bend down, right? And so water has a bent shape. Now, it's really super important to understand that water is bent, okay? And you should draw water as a Lewis structure in its bent shape to get this polarity for water down, okay? So the question is, are there dipoles? Well, between hydrogen and oxygen, there is a dipole that exists because oxygen has a greater electronegativity value than hydrogen. There is going to be a net dipole that's the arrow is going to point towards oxygen. Now, if you look at the other oxygen-hydrogen bond, there is also a dipole there, and it is also pointing to oxygen, right? And so we have two dipoles, both pointing in the same direction. And even though it looks diagonal, we're going to use the up direction. So ultimately, both dipoles are pointing in the same direction. So if both dipoles are pointing in the same direction, it is going to be a polar molecule, okay? If they're pointing in opposite directions, it'll be nonpolar. So water is a polar molecule, and we would actually write that down. Water is polar. Now, because of that, as a result, it's got to form positive and negative poles or ends. So because there's going to be a greater electronegativity on this oxygen, and both arrows are pointing towards it, oxygen is going to be partially negative. And so there's going to be a negative charge region around that oxygen, okay? For the hydrogens, they're going to be partially positive, okay? And therefore, down here in this part of the molecule is going to be more positive. And so therefore, we create our two poles, our negative pole and our positive pole within the molecule. And so overall, the molecule is polar. You can see that by our distribution here, where oxygen is there and our two hydrogens are here. Where the blue is, you can see the small electron density on the two hydrogens and the large electron density in red of the oxygen. So our dipole, this area here is going to be electron rich, and down here it's going to be electron poor when we get our dipoles, okay? So the key is to draw those dipole arrows and to see if those dipoles are going to go in opposite directions or the same direction. If they're going in the same direction, you got a polar molecule. If they go in opposite directions, you got a nonpolar molecule, okay? Now, let's do something for argument's sake, okay? Let's do a hypothetical. Now, this is not real, okay? All right, let's say, though, that water was linear, okay? What if water was linear? So let's say that these lone pairs really did not cause the shape to be bent, okay? What would be the direct consequence of water being linear and not bent, okay? Well, where's the dipoles? Well, there's going to be one pointing in this direction towards that oxygen and a second arrow pointing to the oxygen as well. So both arrows are pointing to oxygen, but one arrow is pointing to the right, right? And the other one is pointing to the left. And so since both arrows are pointing in different directions, they would offset one another. And therefore, water in a linear form would be nonpolar, all right? And so therefore, it would not have a permanent dipole or a dipole that would exist, and therefore there would be no positive and negative region, okay? Now, it's good that this doesn't exist because honestly, the polarity of water is critical to life on Earth. If water did not have a dipole and it did not have positive and negative regions, then water would be useless for living systems. In fact, it is the key and fundamental idea of being able to have life on planet Earth in the first place. Water is absolutely critical, and the critical nature of water is because of its polarity, not because it's made up of hydrogen and oxygen, but because it is a polar molecule, all right? And just think of it, it's all due to the shape. If it was linear versus bent, just that one difference is the difference between having life on Earth versus no life on Earth, okay? So we're grateful that water is bent and polar, okay? So there's kind of a thing there to think about with the shape of the molecule and how it does affect the polarity there. Okay, now, on our last lesson, we went ahead and we actually drew the Lewis structures for these compounds. So you can actually draw them in again, or go back to the previous lesson. But what I'm going to do is go to the board now, and I'm going to actually draw the Lewis structures for these on the board, and you can fill them into the boxes here. But then what we're going to do is we're going to look at the shape, and we're going to look at the polarity of basically these different structures, and see if we can figure it out. Okay. All right, so I'm going to reset things up here. Hopefully this will work. All right, there's our board. All right, so I'm going to use the cheat sheet here because I can't remember which ones we had here. Okay, so we're going to just start with our first one, and that is CCl4. Okay. Okay. Now I'm just going to quickly draw the Lewis structure for it. You're going to have carbon, chlorine. The chlorines have lone pairs. Another chlorine, lone pairs. Draw it this way, and then this chlorine, lone pairs. Okay. So there's our compound. Now, what is the shape of this? Well, it has its 4 bonding domains. This is a tetrahedral shape, okay? And I've got it arranged in that tetrahedral idea, okay? So now what we're going to do is look at the bond polarity and then determine if the polar bonds eliminate or cancel or offset one another, okay? So between this carbon and chlorine, chlorine is more electronegative, so I should have a dipole arrow towards the chlorine. Same thing with this chlorine, same thing with this chlorine, and the same thing with this chlorine, okay? So all my dipole arrows, which I should have 4 of them, all point towards the chlorine, okay? Now the question is, do any of these dipoles offset one another? Well, this dipole is going in this direction, and this dipole is going in the opposite direction. So these 2 dipoles cancel one and out. Okay, so far, all the polarities canceled out. Well, what about the other ones? This one is pointed down, this one is pointed up, so therefore they are also going in opposite directions. So this dipole overall eliminates. So what that tells us is that CCl4 is non-polar. Okay, a non-polar molecule. All right, let's look at the next one. NF3. All right, so it's going to have a Lewis structure that looks like this. Here's my lone pairs. All right, now this is going to be pyramidal in shape because of these lone pairs that are on this nitrogen. It's going to create that pyramidal look towards it, okay? So now let's look at the dipoles as I draw on the arrows, okay? Well, the nitrogen and the fluorine is more electronegative. So we're going to have a dipole towards the fluorine, dipole towards this fluorine, and one between or to that fluorine, okay? All the fluorines are more electronegative than nitrogen, so we have dipoles. Now they're all pointing in the downward direction. Remember, we're either going to point up, down, left, or right. No diagonals, okay? We're not going to deal with that. So since they're all pointing down, none of these dipoles are being canceled out. So therefore, this is a polar molecule, okay? See how that works so far, hopefully? All right, SO3. Now, there are several resonance structures that can be drawn for SO3. I'm only going to draw this one here. That we've talked about, this one here. And we'll look at what's going on with this one here, okay? So this is a planar structure, okay? Planar. So think about that, right? It's got 3 domains. There's going to spread out to 120-degree angles. Being planar now, let's look at the dipoles. Between oxygen and sulfur, which one is more electronegative? Oxygen is. So we have a dipole towards this oxygen, a dipole towards that oxygen, and a dipole towards that oxygen, okay? Now, in a planar structure like this, all the dipoles are going to cancel out because they're pulling in opposite directions with same magnitude, okay? So in a situation where we have a planar, trigonal planar structure in this regards, the bonds, as long as these are all the same magnitude, pulling in the same magnitude, it's going to cancel out, and we're going to say that this is a nonpolar structure, okay? This is nonpolar, right? The only way that this could be polar is if this was something different. Say it was, well, fluorine, okay, something like this. Then the fluorine's pulling with a greater electronegativity, and so this would be slightly polar because the pull, the magnitude of the pull is slightly greater here than it is for the oxygens. But as long as this is oxygen, and this is, as long as these are the same atoms, the magnitude of pull is the same, therefore they're offset, and this is going to be non-polar. Okay? All right. We can even look at another Lewis structure, right? We can look at this one here this is another resonance structure, right, of SO3. So the question here, does the polarity change? And the answer is no, because we have dipoles there and a dipole there. And therefore, this planar structure, the dipole magnitudes are the same. It doesn't matter that this is a double bond at all. Okay, the dipole there is all that matters, and therefore this is a nonpolar molecule, no matter how you look at it. Okay, even with a different resonance structure there. All right, let's do H2S. Okay, so SH like so. It's bent very much like water. Dipoles are going towards sulfur. They're both going in the up direction, and therefore this is a polar molecule. Okay, so polar. Right. By the way, here's a hint about something. Okay. Now this works most of the time, not all the time, but pretty much most of the time. Okay. If you're ever caught or you're in trouble about the polarity and you're trying to decide if it's polar or not polar, and you're just not sure, okay, here's something you can think about. If there's lone pairs on the central atom, if there's lone pairs on the central atom, the molecule is usually polar. Okay, there's just a little hint there. Now, it works 99% of the time, but there is that one little percentage that sometimes it doesn't work. So if you're really in a bind and you're not really sure, go ahead and look at that central atom. If there's lone pairs on that central atom, take your guess, it's probably going to be polar, okay? Because 99% of the time you're going to be correct, okay? It's just a secret. All right, let's look at another one here. SO4 2 minus, okay? So let's just look at one possible resonance structure here. Here's Okay, this is an ion, so we need brackets. Okay, shape, tetrahedral, right? Tetrahedral. Now, we just got done saying oxygen is more electronegative, so all these dipoles are pointing towards oxygen. Notice these two dipoles cancel out, these two dipoles cancel out. So overall, this is a non-polar molecule, okay? There's also no lone pairs, as you'll notice, around that central atom, okay? So this is non-polar. And again, I know I'm not showing all the resonance structures for these particular molecules for time's sake, but you can go back and look at them. All right, next one, NH4 plus. So you got nitrogen, hydrogen, 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 and hydrogen. And it is an ion, positively charged. Okay, dipoles are all going to be pointing towards nitrogen. Nitrogen is most electronegative. So do they cancel out? Yes, they do. These two cancel out. They're pointing in opposite directions, up and down. These two cancel out. That's pointing left and right. So therefore, NH4 plus is non-polar. There's no lone pairs either. Okay, again, kind of see that. All right, let's look at NO3 minus. Right. So again, there are Lewis structures or resonance structures for this. I'm only going to show the one. All right, and this is an ion, -1 charge. Okay, dipoles, oxygen is the strongest. All right. So what's our shape? Well, it's a planar. And what do we say about planars? Planars are going to probably be non-polar. And again, if you're in doubt, there's no lone pairs on the central atom, okay? So therefore, this is a non-polar molecule as well, okay? All the dipoles are cancel out in this trigonal planar, okay? All right, let's move on. ClF3, okay? So Cl, and then we have F, and then F, and then F, and we have some lone pairs here, okay? Now, this is a T-shaped molecule, okay? This has an extended octet. It is T-shaped, all right? Therefore, the dipoles are going towards fluorine, all right? Now, do they cancel out? Two of the dipoles do, right? This dipole and this dipole are going in opposite directions. So this cancels out, but this dipole does not, right? There's nothing to cancel out the upward dipole, nothing going down. So therefore, this is a polar molecule. Even though these two dipoles cancel out, this one does not. And now look at, we have some lone pairs on that central atom. As I said, 99% of the time, if you have lone pairs on the central atom, it's probably going to be polar, okay? And indeed it is, and this upward dipole is not being canceled out. So, oh, by the way, so this would be slightly negative, right? And down here, so this is our negative region. Down here would then be our slightly positive region, okay? I probably should put in those negative and positive regions. All right. But it is polar, all right? All right, let's do SCN minus, okay? We're only gonna do one resonance structure here. Let's do CN and S like so, all right? And this is gonna be -1 charge. Now overall, this is linear, okay? This is a linear shape. But what about the dipoles? Well, there's going to be one going to this sulfur here, and this nitrogen is more electronegative than the carbon, so there is a dipole here. Well, you're going to say, okay, the dipoles must cancel out. Well, wait a minute here. this is nitrogen and this is sulfur, okay? Are they going to pull with equal magnitude, with equal force? The answer is no. Sulfur is slightly a little bit more electronegative than nitrogen, slightly. Not a big difference, right? So this molecule is actually slightly polar, okay? It's a little bit polar, okay? Not a lot though, right? So we would probably consider it polar, but very small in its polarity. There's no lone pairs on it, so this is one of those things that can't really use the lone pair idea, but then still at the same time, this is close to being nonpolar, okay? All right, but yet it still is polar, by the way. Okay. Got that cleared up. Okay, SEF4, okay, so selenium is in the middle. And we got those lone pairs. Then we got there. Ooh, interesting, right? Okay, selenium violating the octet rule. It's got an extended octet here. Okay, so the question is, what's going on here? Well, we got a dipole here, a dipole here, a dipole here, and a dipole here. Okay, but this is where things get a little bit challenging, right? Because the question is, what about those lone pairs? What are they doing? Okay, well, those lone pairs are actually going to create a situation, okay, where these dipoles are not really being canceled out very well, okay? So here we go with an example of these lone pairs helping us to actually determine that this molecule right here is slightly polar, okay? I really like to use that idea of lone pairs on the central atom to help you with its polarity, okay? Especially with these extended octets, okay? There is going to be one that doesn't work so well with this, okay? But in this case, this is going to be a polar molecule. It's got those lone pairs, and in reality, the dipoles are not canceling out so well here, okay? All right, now let's look at another one, CI4, okay? So here we have okay, this is tetrahedral in shape. Carbon is the most electronegative. So they're all pointing towards carbon. There's no lone pairs on that central atom. This is going to be nonpolar. Okay, so this is an easy nonpolar one to distinguish. Okay. All right, now last one, xenon tetrafluoride. Okay, now this is where the lone pairs comes into a problem. Okay, so you have something like this, this, and then we actually have lone pairs on those sides. Okay. The problem with this is that I'll tell you right now, it's going to be nonpolar. All right. The fluorines are indeed going to cancel out each other. And you're going to say, well, there's lone pairs. The problem is in the molecule, the way it's arranged around the central atom, these lone pairs also are going to sort of cancel each other out as well. And so overall, this molecule is going to be non-polar. And it's a square planar, right? And all square planars are going to be non-polar. So almost think about a lot of planar structures, whether it's trigonal planar or whether it's square planar, many of them will be nonpolar. Okay, so yes, I know it has lone pairs, but in this situation with the square planar structure, it's going to be nonpolar. Okay. Polarity is not always easy to determine. I'm going to tell you right now that students struggle with this at first to try to determine if something is polar or nonpolar overall. Okay, do your best that you can. Okay, draw the Lewis structure, create the correct shape, draw on the dipole arrows, look at the central atom if there's lone pairs on it, make all of those kind of deciding factors to determine the overall polarity of the molecule. Remember though that the square planars here are going to be nonpolar, okay? Even though that they have those lone pairs. This is that 1% usually that kind of doesn't go along with our lone pair idea, okay? So there we go. Yeah, that's it for this lesson, really. I would go back, relook at these structures, make sure that you can figure out their polarity, and we'll practice some more of this, of course, in the coming days. So that's it for right now. Good luck, and we will see you next time, okay?